In this chapter, we're going to be talking about how we can blend together balanced chemical equations along with the concepts of molar masses and Avogadro's number all into one type of question, which we call stoichiometry. And stoichiometry is how we look at the math that occurs within a chemical reaction, how 12 grams of carbon might react with oxygen and make, X grams of this. We can actually predict exactly what should happen. But the first key is seeing that every balanced equation is actually a mole-to-mole ratio. So every single equation we have that is balanced, has to be balanced, is written in terms of moles. So this equation right here, with carbon monoxide reacting with hydrogen to produce, this is methanol, which is a very flammable liquid. And the ratio between the carbon monoxide and hydrogen is 1 carbon monoxide reacts with 2 hydrogens. We could actually write this as a mole-to-mole ratio. So here they are. Here's the ratio written as 1 mole of carbon monoxide for every 2 moles of hydrogen. Or we could write it the other way around. There's 2 moles of hydrogen for every 1 mole of carbon monoxide. And all that is I'm using the coefficient, this 1 and that 2, to write them as a ratio. So every balanced equation is really representative of the ratios of moles in the reaction. So the ratio from hydrogen to methanol would be 2 to 1. And the ratio of carbon monoxide to methanol would be 1 to 1. And that's 1 mole of carbon monoxide and 1 mole of methanol. So here we are using the mole-to-mole ratios to convert from one thing to another thing. So let's say someone has 4 moles of water and they want to know how much hydrogen they could produce, or they want to know how much oxygen they could produce by decomposing this water with an electric current. Well, we have 4 moles of water. Here's the ratio from hydrogen to oxygen. So that's the hydrogen value, and that's the water value. And so we're just writing it in there. Now, we're using dimensional analysis, so does it make sense the water's on the bottom? It should make sense because we have moles of water to start off with. This is our given, 4 moles of water. And we want to cancel out the given's units by writing them on the bottom, and whatever new unit we're converting to needs to go on the top. So 4 moles, 2 divided by 2 would give us 4 moles of hydrogen. In the other example, we have 4 moles of water. We're trying to figure out how much oxygen would be produced. It would be 2 moles of oxygen. And this is essentially the new big step that we're going to talk about in this chapter. It's going from moles of one compound to moles of another compound. And just like all stoichiometry, the real key is setting the units up in the right place. Taking the givens units and canceling them out in the next step to change over to a new set of units. And the only thing about this is our units actually come from the balanced equation. So here's our last example. We're going to try to figure out if we have 5.8 moles of water being decomposed, how many moles of oxygen are produced. So we start off, we're just going to write down our given, 5.8 moles of water. Okay. Now let's see, we need to cancel that out, so we need to put moles of water on the bottom. Moles of water. And what are we trying to convert it to? Let's see, it says we want to know moles of oxygen. So let's set this up here. I'll draw my dimensional analysis lines. There we go. So moles of water on the bottom, moles of oxygen on the top. I still need to fill in those numbers. Where do we get the numbers from? That's right, we go back up here. It says 2 waters. This is 2 moles of water right there. Put 2 there. And the oxygen is, there's no number written there, so that's an implied 1. So 5.8 moles of water. We have a 1:2 ratio between the water and the oxygen. So it looks like 2.9 moles of oxygen should be produced. That's essentially the new thing we're going to be doing, is using moles to convert to other moles. Here's our last question before you start working on any of the questions there in the video. You have 4.3 moles of propane, C3H8. You're supposed to calculate, let's just underline the actual question, calculate the number of moles of oxygen. So again, we're looking for oxygen. So here's the oxygen right there. So wrote down the given, 4.3 moles of propane, 4.3 moles of C3H8 propane. And this implied 1 there means there's 1 mole of propane reacting with 5 moles of oxygen. So we're going to need, for 4.3 moles of propane to burn properly, we're going to need at least 21.5 moles of oxygen for this reaction to burn properly.